that we used, those were all very good at slow speeds, okay? As long as you stay below 10% of the speed of light, all those formulas that we learned, all those fundamentals of physics, those Newtonian principles of physics that we learned over the past year, including Maxwell's equations in electricity and magnetism, all work fine until you get going really, really fast, or you deal with things that are very, very big. You know, like things the size of the sun, galaxies, things like that. Okay, then all of a sudden this mass energy equivalence takes place and shows, now this shows the kinetic relativistic energy is given by this. And I don't really like at this level using the gamma thing. I want you all to get used to knowing that that is equal to the square root of 1 minus v squared over c squared, or v over c and squared. And so you kind of get used to looking at that. So one of your homework problems actually deals with this, and then the rest, okay, so for the classical expression, as you can see, as we get closer and closer to the speed of light here, as we get closer and closer, then the classical expression of the kinetic energy does not reveal at all what the actual kinetic energy is of the thing, okay? All right, once we go, when we get up here around 0.4, see how this starts to split? If I had just regular, if I said, okay, a photon is traveling at or one of those items that was talked about in that one little TED video that I showed you with Brian Cox, the particle physicist, when he talked about that they're going to accelerate 2 protons at 0.99 or whatever he said. I think he carried it out to like 7 times 0.99 the speed of light. Then these measurements here would not be valid. They'd go, wait a minute, we're measuring the kinetic energy of those protons as being way up here because they're approaching here, so it's the kinetic energy of them is almost going to infinity there. Okay? So you had to account for this thing when things are going very, very fast. Okay? And then there's the relativistic momentum also of something. So you can see that if something is going at the speed of sound, which is 300 meters per second, that's 3 times 10 to the second, right? And this is 3 times 10 to the 8th. Well, if you square this when you wind up with 9 times 10 to the 4th, you square this when you get 9 times 10 to the 16th, you divide those two, what do you get? Pretty close to 0. So even at the speed of sound, relativistic things, considerations don't need to be taken into consideration. All right, and we'll discuss a lot more of these in Physics 350. For those of you brave enough or have the time, I know most of you are still taking 19 hours just to get through your double major in chemistry and biology and all that kind of stuff. So it comes down to there's not enough hours in a day to take all the stuff that's really cool around here. But anyway, and so the total energy of a system is given as this. And let me do one of the problems. Let's just do one of the homework problems that you have that some of you are having trouble with. And I'll have to read it out of the book. Then we'll get into the cool stuff, and we'll talk about black holes and anyway, and then we'll talk about relativistic addition and a few other things. But let's go look at that one problem that I gave you. It says how much, wait, what was it? Okay. Okay. Let me go find, hold on one second. I hate to have to do this, but I've got to. Sorry. I apologize. I got to go to Mastering Physics to find it because I can't find it here in the homework problems. This is one where you had to get 1.5% or something like that. Yeah. Right. Okay, for some reason I can't find the equivalent problem. I don't know. All right. Anyway, my mistake. Sorry. Okay. All right. Okay. Courses. This is you all. Let's go to the. Hopefully this thing is working. I was having trouble with it working in my office here. All right. Last one. There we go. Now. Oh, I already did it. Is this the one before that? Oh, yeah, I wanted to do that one too. Okay, 26, 24. How come it doesn't look like... Oh, there it is. Okay. There it is. This is problem 24. All right, now then. Here's how you do this problem. Well, which one is it? Let me find it again. Come on. God. It's been one of those kind of days. Okay. There we go. All right, let me rework it so that you all can see it. Standard view, rework. Restart and work. All right. Let's see what pops up here. Okay, here we go. Now it's going to be a little bit different problem. It says, how fast must an object travel for its total energy to be 10% more than its rest energy? Okay. All right, so what we want is how fast should an object be traveling? And what we've got is this. So we want 10%, and then again when it's at 90%. All right, so we can deal with this now. There we go. So how fast should it be traveling when it's going at 10% or at, the first one's at 10% of its rest energy. So that would mean, whoops, so here we go, 10% of its rest energy. So that would mean that E equals K plus E naught. Whoops. I don't know why I put the 10 there. It's because that's the kind of day I'm having. All right. Now then, so the total energy is equal to this. Now we know this. We know that what we want is we want 1.1 of E naught equals K plus E naught, right? That's what we're up to so far because it said how fast must it be going if its total energy if its total energy is going to be 10% greater than its rest energy. So that's what we've got so far. That was the key to that. And so you wind up with K then equals 0.1 E naught. Now this turns it, now like I said, what you want to do is you want to go ahead and do all the algebra first and then plug in the things. And we know this. We know that K is equal to what? 1 over the square root of 1 minus v squared over c squared minus 1 times mc squared. Okay? And that's going to equal 0.1 mc squared. Because E naught is equal to mc squared. All right. Well, right off the bat, what's something we can do? We can cancel out the mc squareds. Boom. Divide this by mc squared. Divide this by mc squared. So there we go. So now we've got 1 over 1 minus v squared over c squared minus 1 equals 0.1. Okay? And so now, get 1 over 1 minus, I do it different every time, equals 1.1. Let's flip that over and square both sides. So I've got 1 minus v squared over c squared equals 1 over 1.1 squared. Don't forget to do that because that'll screw it all up if you don't. So I wind up with 1 minus 1 over 1.1 squared equals v squared over c squared. Oh my. And then, using that, and so basically I wind up with 1 over 1 minus 1.1 squared times c squared equals v squared. So you take the square root of that guy, and you wind up with what your v is in terms of c. Oh, so we've got kind of a pattern here. So you take 1 minus, and OU of little faith. Let's see if this actually works. Now, I'm going to actually show you how I would punch this in on the calculator. I think you can kind of see it there. Yep, I got to move it off to the side here. Now, here's how I would do this. I would take second and the square root, and then I'd hit this again and go 1 minus 1 divided by, and I'd also hit this in parentheses, 1.1 squared, and close that parentheses, equals. There we go. That'd be 0.416. Let's see if that works. What's that? Yeah, that's the multiple of the speed of light that we'd have to go, because that's what it's asking.
Multiply by the speed of light, make that speed right by your square root, outside your square root, because you're solving for v.
Uh-huh.
So
it's 0.41. What?
Oh, but it's in terms of c.
It's in terms of C.
Oh, okay.
Yeah, there you go. Yeah, the answer is going to be in terms of C here. So let's see if 0.416 works, or what do they want, 2 sig figs? I'm going to go crawling in shame. We're going to cancel class. This is wrong. Uh-oh, shouldn't have said that, because you never know about this guy. Ooh, it's taking time, so that means it's probably right. Yes?
Where'd you get that 1.1?
What's that?
Like 1.1.
It said it wanted 10%. It's going to be 10% greater. And so 1 plus 0.1 comes out to be 1.1. All right, now, so since we have that idea, since we have that kind of general, and you have confidence now because we tried it once that this is going to work, then if they wanted it 90%, what would we do? What's the only thing we'd change here?
It's 90% more.
Yeah, it's 90% more, so what would we change this to? 1.9. Boom. And you got it. And you're going to find out that the speed of light then to get it up to 90% more is pretty big. In fact, let's do that. I can just go, now, the other nice thing I can do, so those of you that have 10% and 90%, you're living large. Those of you who had 5% and 95 like I did, you have to do this again, but you can see how it works. All right, but anyway, if I go second entry, I let my calculator do all the work for me if I can. But to do that, you've got to really be careful with your algebra. 0.85% the speed of light. Let's see if that's correct. And I got 0.85. Boom. Yes, it is. Okay. All right. Yeah. No. You can't. There you go. Come on. There it is. See, I did it all I know the math and chemistry departments are still living in the 70s, and they don't let you use these calculators. Why, I don't know. Because you can program them. Oh, that means you're studying. Oh, well. But anyway, I've never understood that. But anyway, I've gotten spoiled. I have to use this kind of. I think you can do it on the scientific, but you have to be very careful. You've got to take it one calculation at a time and write it down each time. And no matter what, on a calculator, you still have to know your algebra. Otherwise, you can.
The previous one with the kinetic energy, I think what I'm getting confused with is converting it to joules.
Oh, it wants it in joules.
I know that's what's bugging me.
Oh, is that where an electron travels at a speed of 0.6 c? What is its total kinetic energy? All right. Let's take a look at that. Here we go. This is where the kinetic energy, now once again, the answer will be in joules.
I know, right. For some reason I'm getting in my electron volts.
Oh,
But MVE, my answers comes out there.
do they want it in MVE? No, they want it in joules. That's right. So it says, hey, what's K? What's K if V equals 0.6 C for an electron?
We can't say.
For an electron. Whoop, you can't see that. It's a mystery problem. There you go. We've got it out of its black hole, which we'll talk about here in a minute. There we go. Now, here's what that would look like. All right, so the kinetic energy again, K is equal to 1 over 1 minus v squared over c squared minus 1 times mc squared. All right. Well, we just plug 0.6 in here for this. So you take 1 over, now this time I'd actually plug in the numbers first. 1 divided by 0.6 squared c squared over c squared. That's nice. That means my c squareds cancel. Minus 1 times mc squared. All right. So now, here's what I do. I'm going to go ahead and put my calculator up here. Maybe you can see both things there. Maybe you can't. All right. So here's how I do this. I take parentheses. Well, I'm just going to do this term here anyway, so it doesn't matter. So I go 1 divided by the square root of 1 minus 0.6 squared, close that parentheses. And that equals, and then minus 1 equals that. Now I'm going to take 0.25 times mc squared, where we know that by the way, do y'all remember all the way from chapter 15 what the mass of an electron is?
Wasn't MC squared like 0.511 m?
No. What's mc squared? What is, I see what you did. You looked in the book and found out what the kinetic energy, you could have just taken that answer divided by 1.6 times 10 to the negative 19 and gotten the joules. Yeah. But anyway, yeah.
Before we go any farther, what does the total energy be the kinetic energy plus the rest energy?
No. Are they asking for the total energy? I thought they were asking for the kinetic.
They asked for both.
Oh, okay. All right. So they asked for the kinetic energy and what is the kinetic and total energy? Oh, yeah. Okay. So they asked for the kinetic, and then we'll add mc squared to this and get. So basically, the total energy, E total, is equal to 1.25 mc squared, and this is equal to, and then K is equal to 0.25 mc squared. Okay. And too bad it didn't put mc squared off into the corner, but it didn't. So we've got to, which is in joules, because you think about it, remember, 1/2 mv squared, remember that? That was in joules. So this is also in joules. All right, so anyway, my quiz question was, it's not a quiz, but 9.11 times 10 to the negative 31 kilograms. Okay, so you take that, you take your answer times, and I always put my scientific notation guys inside parentheses just to avoid any kind of, and then times, again, 3 second e to the 8th, close, squared, close, boom. There it is. That's about right. That should be about 2.05 times 10 to the negative 14th joules. Now, if you'd have taken that electron volt thing and divided by 1.6 times 10 to the negative 19, you would have gotten the joules. Or multiplied it by 1 point. You had to multiply by 1.6 times 10 to the negative 19. Yeah. And then basically add mc squared to that for that little bitty photon. Or if that's 0.25 of it, multiplying by that's the 1.25, so to get that to, yeah, thank you. 5/4. Very good. And then times 5, thank you. Bailing me out there. Here I was making my big speech about algebra, and I couldn't do it. All right, but anyway, there you go. All right. Okay, I didn't want to spend that much time on it, but hey, we got 2 of them knocked out anyway, so there you go. All right, now, let's go ahead and look at some things here on black holes, special relativity, and okay, here's the thing on, whoops. Right.
In fact, scientists needed nothing more than Newton's equations to plot the course of a rocket that landed men on the moon. Yet, there was a problem. While his laws described the strength of gravity with great accuracy, Newton was harboring an embarrassing secret. He had no idea how gravity actually works.
Doesn't Newton look like a lead singer in a hair band? That's something I was thought. Kind of looked like a guy from Poison or something 50 years later. I've got to see you. I forgot all about you the other day.
Working in the Swiss patent office would change all that. While reviewing patent applications, Albert Einstein was also pondering the behavior of light. And little did Einstein know that his musings on light would lead him to solve Newton's mystery of what gravity is. At the age of 26, Einstein made a startling discovery that the velocity of light is a kind of cosmic speed limit, a speed that nothing in the universe can exceed. But no sooner had the young Einstein published this idea than he found himself squaring off with the father of gravity. The trouble was, the idea that nothing can go faster than the speed of light flew in the face of Newton's picture of gravity. To understand this conflict, we have to run a few experiments. And to begin with, let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears. Now, let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space. In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory. A problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes? To the young upstart from the Swiss patent office, anything outrunning light was impossible. And that meant the 250-year-old Newtonian picture of gravity was wrong.
If Newton is wrong, then why do the planets stand? Because remember, the triumph of Newton's equations come from the quest to understand the planets and the stars. In particular, the problem of why do the planets have the orbits that they do. And with Newton's equations, you can calculate the way that the planets will move. Einstein's got to resolve this dilemma.
In his late 20s, Einstein had to come up with a new picture of the universe in which gravity does not exceed the cosmic speed limit. Still working his day job in the patent office, Einstein embarked on a solitary quest to solve this mystery. After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the 3 dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity. A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it as Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears.
So therefore, the universe is flat.
Disturbance that results
It's completely flat and infinite. And
that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light. And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. It warps and curves in the fabric of space and time.
okay,
Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
all right. So anyway, he became basically a rock star, I think is what they said. Now, secondly, now one of the things. So when he was a young man, he got this idea. He's like, well, if I'm in an elevator that's accelerating really, really fast, then the light coming in, and this is kind of illustrated in your book, but then the light coming in one window of the elevator, if I'm accelerating, then it will look bent to me. If I'm in a rocket ship going up, then the light that just enters the window should bend down and hit down here. I mean, it should be bent, right? If I'm moving up, then it should bend down. So, but we couldn't find that on Earth at all. There was no way to replicate, something accelerating that fast so that you'd accelerate it from 0 to the speed of light within a short amount of time. And so there was no way to prove it until there was a total solar eclipse, and we were able to pick out two stars, and we saw that they were actually the light from these stars was bent, that our sun did bend them. So it was kind of that verified in the lab. Remember, you can have all the theories in the world, but until you start verifying them in a lab, basically all you have is a philosophy then, all right? So, and that's one of the problems with string theory right now is it's a great idea, and mathematically it all works out with these 11 dimensions and all that kind of stuff, but we haven't been able to devise experiments to do. And the lab can be the universe, I mean, with the pictures you're taking with Hubble and various other things, but they haven't been able to verify any of the stuff. So anyway, talking about black holes, I think in your book they came up with this, they showed you, and we'll go to it now. They showed you some things on the Schwarzschild radius. But it said the Schwarzschild radius is equal to this for a black hole. And you've got a couple problems that deal with that. All right. Yeah, there you go. So the escape velocity is something. The escape velocity, like to get away from the Earth, and I wish we'd have gone over this a little bit more, or to get away from the sun. Whoa, there you go.
That's number 7, the last question.
Okay, now then, the escape velocity to get away from something, and believe it or not, good old Newton's capital G universal gravitational constant is still being used, but we've calculated, we should have calculated that the escape velocity to get away from something is equal to 2 times g times the mass of the object we're trying to get away from divided by the radius of the object, or how far we want to get away from it. And so for a black hole, this is what Schwarzschild came up with. He said R is equal to 2gm over c squared. Okay? Because let me go over what a black hole is again. What it is it's where light enters in and bends into it, spirals into it, and doesn't reflect out. Okay? So we can't see anything there. Now, astronomers, because of the use of Hubble and all these relativistic ideas and some quantum ideas also, have theorized now, and they're putting it to the test. They're doing it in their lab using the Hubble telescope and a few other things, that each galaxy, at the middle of each galaxy is a black hole that it's spiraling around. Okay, so there's billions of galaxies, so there's billions of black holes out there. And this gives you at R, this gives you the event horizon. All right, in other words, as things get closer and closer to that, you can still see them, there's still light, and then all of a sudden, phoom, they're not there anymore because they're inside the event horizon. If you crush down the Earth, if you did this for Earth, I was going to do it real quick, but then I found another video that told me real fast what the answer was. If you did this calculation for Earth, you'd find out that Earth could be its own little black hole if you shrunk it down to about the size of your thumb. All right? If you took the entire mass of the Earth and smashed it down to about the size of your thumb, then the Earth would have a black hole. Okay? And in other words, the radius of it would be about that big. Okay, about the size, the R that you come out with there would be about that big. So it's pretty small, very, very, very small. All right. So without further ado, I think one of your homework problems, in fact, your last one, which we'll talk about next time. I've got to do this. All right, real quick. Ting-Yi, we're done pretty much with filming. I'd like for you to stay and fill this out if you could. If you can't,